we're going to be looking at here are spring potential energies. Often I write this as US, U being our potential energy variable, S being a spring. And we're going to look at spring potential energies and the equations that kind of go behind them. We remember back, well, if you don't remember, go check out some of the other videos, that we have a spring force, Fs, equal to negative, and that negative is a restoring force, so sometimes we just don't even bother writing it in, and we just look at our free body diagrams of what have we called positive, what have we called negative. But we have this negative, and then kx, where k is a spring constant and x is an amount of stretch or compression of the spring from its rest position. The rest position being where the spring just naturally wants to be. If that force is there, though, then what we can do if we wanted to figure out how much potential energy do we store in a spring. Because if you have a spring, if you stretched it out and left it there, it wants to snap back. That's what it wants to do. But you can stretch it out and just, pin those ends in place, and it will stay there. There is some stored energy now in the spring. It wants to go back to where it was. So if we take a look at a graph here, if this is a force position graph, so this is a work graph, because we remember that if we have Fx, that's getting some useful amount of work out of this. And that's similar to the idea of energy. Work energy we know goes together. If I have a force position graph and I plotted kx, then what we would see here is that we would have a linear line like that. The reason being is that for each piece we move on the x-axis over, it gets harder to pull the spring. At some point you're really trying to pull that spring, but it's just too much, and it pulls you back. So what we have here is this linear graph going positively upward, and if we wanted to find the amount of work done here, well, we know that work is equal to F dot technically, but let's assume that we're pulling along the direction of the spring stretching. So we can just say that this F dot delta x is really just Fx. But we can't just use Fx in a problem like this because the force is changing. We need an area. If we look at this area here under the curve, that's a fairly simple shape. It's a triangle. It's 1/2 base times height. Well, if we look here, our base is some value x. So we've got 1/2 of some value x. If we look at our height here, well, our height is dictated by some amount of force. So, well, how do we get the force out of this? We know the force is equal to kx. At this x position, there is some known force. So for our height, we have kx. And if we bundled all of that together, what we actually see as a very useful equation is that the work, or the area underneath this curve, is equal to 1/2 kx squared. And this here is equal to the spring potential energy. That's a huge equation right there. And we did that just with the ideas we've had previously. We know work under a force position or a force displacement graph is the area. If this force is changing by some slope k, the spring constant, the strength of the spring, well then we have a linear line. And if we found the area of that linear line, that's a triangle. Plugging in our bases and our heights here, our x and y axes, we get this amazing equation for a spring potential energy. How much energy do you store in a spring when you stretch it out or you compress it back in? And that's going to be an equation we're going to be using in this unit. But that is how you would derive it. That derivation is finished. Why don't you check out the next video on a 9-C4 problem to see how we can kind of use this in a problematic setup.